So about a century after Dalton proposed his four postulates for atomic theory, J.J. Thompson was doing some experiments with a cathode ray tube. Now, a cathode ray tube is set up like this. You can see that there's going to be a cathode section at the very back. There's going to be an anode with a hole in it. And then there's going to be a big tube that's been evacuated of all the gas present. So it's a nice vacuum inside. Now, we apply a voltage across these two. See that we have a negative charge on the back, positive charge on the front. We'll actually deal with the terms cathode and anode in great detail, usually in chemistry 2 when you're taking the electrochemistry portion of the course. Now, we don't need to memorize those for the time being, but it is worth noticing that there's a negative charge back on the cathode. And there's a beam that's shooting toward the positive side, and it's going through that small hole. Things that are hitting the positive electrode just don't progress any further, but the ones that actually go through that circle in the center, the small hole, are going to shoot out like a beam, and they're going to be hitting the very end where it's got a phosphor-coated glass surface. And you can see that you can set up something like a protractor and you can measure the angle of deflection if you do things to it. This is the scientific instrument that they realized would work for more entertaining versions, and you may have run across the name cathode ray tubes, or CRTs, when you're looking at old computer monitors and old televisions. Now just about everything's a flat screen, but back in the olden days, as my wife likes to say, they used CRTs, cathode ray tubes. Now, what they were doing is just deflecting that beam in order to make the light glow in different spots on the screen and create the picture that you were aiming for. But let's see exactly what they used this scientific apparatus for originally. Now, you can see here that he was able to take a magnet, and when he put it into a magnet, you can see that the beam deflects. And it deflects a decent amount just by putting a magnet. Now, as a child using a CRT monitor, you may have held a magnet from your refrigerator up to the TV and seen the funny things it did for the glow. It was something very similar to that, but the science version. Now, not only does it have some sort of a magnetic field, but that tells us something important. It means that if it's curving the magnetic field in that direction, these particles must be charged. Not magnetically charged, that's not an actual thing anyway, it's electrically charged. So there's got to be an electrical charge on the magnet. So the next thing he tried, at least that we're looking at in the progression, was putting charged plates, a positive plate and a negative plate. And we can see that the beam curled toward the positive side. And we know that opposites attract, so since it's charged and bent toward the charged plate that was positive, the particle itself has to be negative, right? Now here's the really interesting result. Suppose you swap out the copper, we'll just say it was copper, cathode electrode that's at the very back, and instead you put in an iron electrode or a lead or any other metal. It didn't matter what one you used. You had the exact same result. You had the same beam form, it behaved the same way, it deflected the same distance, everything was the same. So whatever particle was being kicked loose from that cathode was the same no matter what metal was being used. That's a pretty big deal. It means that there's something inside of the atom, and it's consistent from atom to atom. That was a really big result. Now, here's the man himself, J.J. Thompson. He did these experiments in 1897. He determined that, yeah, atoms can be broken into smaller pieces, and that electron is far lighter than the lightest of atoms. And from these deflections, he was able to determine some idea of how heavy it was, but he couldn't actually measure the mass. What he was able to determine was the mass-to-charge ratio. Now let me explain why that is. Remember that he doesn't know the mass, and he doesn't actually know the real charge on the electron at this point. But he's able to see that it's deflecting a certain curve, right? Now, if it was supposed to go in a straight line, but it curved this much, he's able to say, well, it was pulled with a certain amount of force if he knows the weight. He doesn't know the weight, though. If you have something that's very heavy, but moving very fast, it can go on the same curve. If you have something that's very light and moving fairly slowly, it can be curved as much. If you picture something that's much lighter but going faster, it's not going to deflect anywhere near as much. Since they're curving the same amount, he's able to determine all of them have the same mass-to-charge ratio, but he wasn't able to measure what the mass or the charge was. Still a big result, because if someone else can find the mass or the charge, we get both values. Now, these pieces aren't called electrons yet, and we aren't really bringing them up in the context of electricity yet, although that comes up fairly soon after this. Now, the big thing is, at the time, Dalton's theory had taken the day so strongly that people really had this idea that the atom was indivisible. You couldn't get anything smaller out of an atom. It was so entrenched at the time, they thought he was just joking. They thought that this was basically like the Mad Magazine or cracked version of science when he published it. Now, somewhere in the next decade, people finally started coming around to his line of thinking, especially as other people did the same experiment and got the same result. And finally, in 1906, it was an accepted enough result that he wins the Nobel Prize, which is obviously a pretty big deal.